In this video, we're going to start to take a look at some probabilities of binomial experiments. So the probability, if we want to determine the probability of exactly k successes in n trials, we have to take, first of all, the number of different outcomes that we could have. So that was using our choose function. That looks like n factorial divided by k factorial times n minus k factorial. And then we want to multiply that by the probability of a single scenario. So that would be times p to the kth power times 1 minus p raised to the n minus k power. So this formula is quite long, but the second part isn't too terribly difficult to work with. Most of your calculation in this problem, in these types of problems, is really going to be spent working on this choose function, and we'll get some more practice working with those. So for all of these problems, we need to determine, first of all, what is n. So we want to know what is n, how many trials am I running? What is k, how many successes am I looking for? And what is p, what's the probability of success of each one of these trials? So number one says, suppose that we roll a fair six-sided die 4 times. So we are running this trial 4 times. That means n is equal to 4. What is the probability of getting exactly 1 5? So in this case, I'm defining a success as getting a 5. So in this scenario, it might not look like it's a binomial experiment at first glance, because you might say, well, there's more than one outcome. You could get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. But I'm going to boil this sample space down to either it's a 5 or not a 5. Those are the only 2 outcomes, and I'm going to define getting a 5 as my success. So in this case, I want to end up with exactly 1 5, meaning exactly 1 success, and then the probability of success, assuming that this is, a fair die, that probability would look like 1 over 6. Let's go ahead and get a decimal for that in place. That would be 0.167 if I rounded to 3 decimal places. So for all of these problems, we need to know what is n, what is k, and what is p. Once I have those things, I'm going to go ahead and plug those values into my binomial probability formula, which I have up here. So that looks like n factorial. So this is going to be 4 factorial divided by k is 1 factorial times n minus k. That's going to be 4 minus 1 factorial times p to the kth. P in this case is 0.167. So 0.167 to the kth power, we said k is equal to 1, times 1 minus p, that's going to be 1 minus 0.167, raised to the n minus k. That's going to be to the 4 minus 1 power. Now, I'm mostly going to spend my time working with this choose function, like I said earlier. That tends to be the part that I'm going to worry about for right now, and I'll come back and worry about the rest of this calculation later. Let's look just at the choose function. 4 factorial, these numbers are relatively small. We can go ahead and just write it out. 4 factorial is 4 times 3 times 2 times 1. In my denominator, 1 factorial is just 1. If we want to simplify 4 minus 1, that's really 3 factorial. So we're going to multiply 1 times 3 factorial, 3 times 2 times 1. And again, we should have a bunch of stuff cancel from our numerator and our denominator. We're left with 4 divided by 1, which is just 4. Cool. There is the choose function. That's what I consider to be the hard part of these problems. Once I have that, I'm just going to bring down the rest of this. I'm not going to bother writing it every single step. The first part times 0.167 to the first power. You don't need to necessarily write that 1 there, since it's just going to end up being 0.167, but we'll go ahead and leave it. Times 1 minus 0.167. Here we will want to go ahead and calculate that out. I have 0.833 to the 4 minus 1, that's to the third power. And then at this point, this is something that we can just go ahead and take and plug into our calculator. So 4 times 0.167 times 0.833 raised to the third, I ended up with a probability of 0.3861 for my answer. I'm going to go and round my probabilities to 4 decimal places. So to be honest, I really think that hardest part about this is still going to be that choose function that we talked about a couple of videos ago. The rest of it, the probability of that single scenario, is not too terribly difficult as long as you take a second at the beginning of your problem to establish what your different variables are. What is n, what is k, and what is p. Let's take a look at one more problem here. Number 2 says, suppose that the probability that a student is admitted to an Ivy League school is about 17%. If 10 students were to apply, what is the probability that at least 2 are admitted? Now, this one, I have to be honest, it is a little bit tricky. It says at least 2. So we need to think about this. This is actually talking about multiple scenarios here. So when we say at least 2, let's actually start by thinking about the number of trials. Let's back up for a minute. The number of trials, which is n, we have 10 students that are applying. So we are thinking about these 10 different students. The probability that each one of these students is admitted, which I'm going to assume is a success here, is 17%, or 0.17. Now, the problem is k could take on a number of different values here. K could be, if I say at least 2, it could be 2 or more. So it could be 2 or 3 or 4 or 5 or 6, 7, 8, 9, 10, all the way up to 10, because that's the total number of students that were applying. Which this seems like a lot, and it is a lot. It's quite a few students. I would have to use my binomial probability formula for every single one of these values for k. And then once I have all those probabilities, I'd have to add them all together. That sounds like a lot of work. That's a huge amount of work. And I'm going to say, well, there's got to be a faster way to do this problem. And I'm going to think about the complement. The thing that really draws my eye here is this phrase, at least. At least or at most tend to be really big clues that, hey, we might want to think about the complement here of at least 2. So let's pause for a second and we think about the number of students admitted. Number of students admitted. So this is just going to be my sample space. If I say this is the possible number of students that could end up admitted out of my sample of 10. So perhaps nobody gets in. That would be 0 students get in. I could end up with 1, I could end up with 2, 3, 4, all the way up to 10. I can't end up with more than 10 because I only have 10 applying. So it looks something like this here. And when we say at least 2, that's talking about 2 or more. Here is at least 2. And we said, boy, that's a lot of work. And I'll be honest, I'm a lazy person. I don't want to do all that work. So I'm going to think about the complement. The complement would be either 0 or 1. So what I can do is I can say, well, what if I found the probability of either 0 or 1? I'm still going to have to do the binomial probability formula twice, add those two probabilities together, and then once I have that, I say, well, that's actually the complement of what I want. I'm going to subtract that probability from 1 to tell me the probability of at least 2. So there's a lot of moving parts here. But what I'm trying to do is I'm trying to make this problem easier for us. I'm trying to say, okay, how can we take this problem that has all of these different values for k and make it a little bit easier? So let's think about a different value for k. Instead of saying 2 through 10, we're going to think about 2 different values for k. We're going to say k is equal to 0 or 1, keeping in mind that these represent the complement of what I'm actually trying to find. So I have 2 different cases. Let's do k equals 0 first. So k equals 0. One quick note I'm going to have to make here. I mentioned this in the choose function for video, but there's one special case for factorials that we're actually going to need to use here, and that's that 0 factorial is just equal to 1. So just keeping that in mind, 0 factorial is equal to 1. Let's start with k is equal to 0. Our probability formula says n factorial divided by k factorial times n minus k factorial times p to the kth times 1 minus p raised to the n minus k. So n factorial is 10. This is going to look like 10 factorial divided by k factorial, that is 0 factorial, times n minus k, that's 10 minus 0 factorial, times p, that is 0.17 to the kth power, that is to the 0th power, times 1 minus 0.17 raised to the n minus k. That's going to be 10 minus 0. So again, I'm going to spend most of my time thinking about this choose function and focused on that right now. And this actually simplifies really nicely, because if I look at this part right here, 10 minus 0 is just 10 factorial. So what I really end up with, I'm not even going to write it out in this case, because I have 10 factorial divided by 0 factorial is 1 times 10 factorial. Well, these two are going to cancel out, and I'm left with 1 divided by 1, which is just 1. So the number of scenarios that I have in this case is 1, and that's that, in this case, k equals 0. Nobody gets into my school. Bringing down the rest of these right here, times 0.17 to the 0th power, that should be 1 as well, times 1 minus 0.17, that should be, what, 0.83 raised to the 10 minus 0, that's to the 10th power. So if I multiply all this out, 1 times 0.17 raised to the 0th power times 0.83 raised to the 10th, I end up with 0.1552 if I round to 4 decimal places. So here is my binomial probability for k. We said k is equal to 0 successes. That's one part of my answer. We also said, hey, we want, for the complement, we want to think about k equals 1. So I'm going to have a separate problem over here where we think about the case where k equals 1. Notice that n and p, the number of trials that we're running and the probability of success, those don't ever change here. We're still using those same values. The only thing that's changing is k. So again, using my binomial probability formula, which is n factorial over k factorial times n minus k factorial times p to the kth times 1 minus p raised to the n minus k power. So let's see, n is, we said 10, so this is 10 factorial divided by k is 1 factorial this time, n minus k, that is 10 minus 1 factorial, times p to the kth, that'll be 0.17 raised to the first power, times 1 minus 0.17 raised to the 10 minus 1 power. Oops, 10 minus 1, make sure we can see that. Cool. All right, again, spending most of my time with this choose function right now. 10 factorial, actually, let's do this first. 10 minus 1, that's 9 factorial. This is the number that I'm going to try and cancel. I want to make sure that I write out to at least 9. So 10 factorial is going to be 10 times 9 times 8 times, and so on, down to 3 times 2 times 1. 1 factorial is just 1. And then 9 factorial is going to be 9 times 8 times 7 times 6, all the way down to 2 times 1. And again, I should have a bunch of stuff cancel out, in this case, which I do. And I'm simply left with 10 over 1, which simplifies, of course, to be 10. So there is the first part. That's the hard part. We just bring down the rest of this probability formula. So 10 times 0.17 raised to the first power times 1 minus 0.17, that's going to be 0.83. 10 minus 1 gives me 9. And at this point, we can grab our calculator and punch this in. So 10 times 0.17 to the first times 0.83 raised to the 9th. This time around, I ended up with 0.3178 if we round to 4 decimal places. This is the case where k is equal to 1. So here is that probability. So I am very nearly done with this problem. The hard part is over. if I wanted to find the probability where k is equal to 0 or 1, that just means I'm going to add these two probabilities together. So 0.1552 plus 0.3178. 0.1552 plus 0.3178. That gives me 0.473. Now, let's take a moment. First of all, let's just take a breath. We've done a lot in this problem. Let's go back and think about what it is that we were looking for. We found the probability where k is equal to 0 or 1. That was the complement of what we wanted. We wanted the probability of at least 2. So we have one last thing to do. This is the complement of the event. If I want to take that and find the probability of the actual event itself, I'm going to take 1 minus the probability of the complement. So to finish this problem up, the probability of at least 2, this would be 1 minus the probability of the complement, which we just found is 0.473. So 1 minus 0.473 gives me 0.527. There is my answer. So these problems can get pretty tricky if we're thinking about multiple cases where we have k equals 2 successes or 3 successes or 4 successes. Keep in mind that as you're reading through these problems, like I said earlier, problems that involve the statement at least or at most tend to be very helpful using the complement. I think taking a moment at the beginning of the problem, like we did up here, to list your values for n and p and k are extremely helpful and will help you think about, okay, what are the different cases that I'm going to have to consider? And then when it comes time to plug numbers into your formula, you've already got them listed. They're right in front of you. So in the next video, we'll probably get some practice working with the graphing calculator. We can use that to help speed up this process or check our answers to hopefully help with the ease of these calculations.